Greetings, good afternoon or good morning, depending on where you are. My name is Professor Duke Orata. We are continuing with our thermodynamic lectures. Today we want to look at a dimensional analysis using indices in solving some of these heat transfer equations. If you recall correctly, we had said that the Nussfeld number was a function of the Reynolds number and the Prandtl number. Always remember that. And we had said that Reynolds number, Reynolds number was related to density, fluid velocity, and displacement of a dynamic viscosity squared. That's density, dynamic viscosity, fluid velocity, and displacement. And we had said that Prandtl's number, again, that is dynamic viscosity, specific heat, and then we have thermal conductivity. And so, solving this problem, this equation here, can be done using differential calculus, where you set up the series of differential equations, you set up and you solve the problem. But you can also use an alternative method, that is dimensional analysis using indices. To solve the equation, we can use dimensional analysis using indices. Now, when you're dealing with dimensional analysis using indices, one of the challenges normally is that you need to know all the variables which are associated with the heat transfer. For example, let us say we want to use dimensional analysis using indices to solve for heat transfer. Each heat transfer in forced convection, that heat transfer coefficient in forced convection. Suppose we are solving for heat transfer coefficient H in forced convection. Remember, from Fourier's law, Q is equals to minus K, the theta dy. But also we had said that this quantity, the same as that heat transfer coefficient where the temperatures, those are the wall temperatures and the temperatures, the temperature where we're the free stream. So we can say that H was minus Q. If we call this temperature difference relative temperature, that temperature difference, with the wall temperature, we can call that theta. Yes. And so we might use dimension analysis using indices to try and solve for that particular equation. Like I've said, you can solve it using differential calculus, where you set up those differential equations and you'll be able to still solve. But we want to look at the dimensional analysis in the solution for this key equation. Like I've already mentioned, for you to use this dimensional analysis, you must be familiar or have an idea which variables are involved in the heat transfer. So it is important to be able to identify the variables involved in the heat transfer. And of course, their units. You need to know their units. So we are familiar with the variables, and I keep encouraging you that continue going through all our lectures. We have used this variable so many times, and we have solved these equations quite a number of times. very many times. And so if we follow the lectures systematically, we will be all in harmony, in synchronized in our movement in terms of solving some of these problems. We know that some of those fundamental variables which have been involved in heat transfer, we can say straight away we have H there, and that is heat transfer. Let me put them variable, and let me put its units. So if we have H, the units of H is watts per meter squared per Kelvin. The other one, which is fundamental, is viscosity, and that is Newton second per meter squared. The other one is, let's say them rho. We can have rho, we can have K, specific heat, mu, and L. This is viscosity, don't forget. This is density. This is transfer coefficient. This is density. The units of density is mass over volume. The other one, K, that is thermoconductivity. And the unit for that is watts per meter Kelvin. Cp is specific heat. The unit is joule per kilogram per Kelvin. We have temperature. Of course, you know the units are Kelvin. We have fluid velocity. The unit is meter per second. And this characteristic dimension unit is length. So these are some of the variables which you are familiar with, in terms of heat transfer. We have used them, we have worked with them, we know them. And those are the units. Because why have we listed the units? We need the units in the dimensional analysis. We need the units in the dimensional analysis. And we have put this dimension because we are thinking of what this equation which we are going to derive can be used in geometrically similar units. We have talked about the principle of dynamic similarity, and we talked one of the fundamental principles there was geometric similarity. So that dimension is critical for use in geometrically similar systems. And if you recall, in our principle of dynamic similarity, we had this body as the field, and this body, and you can call it dimension D. It becomes useful in that particular case. Dimension D is useful in that particular case. So we have that body and we have the field and so forth. We have talked about this in the principle of dynamic similarity. so that this expression get here would be used in geometrically similar systems. Now, one of the things which we need to know is that in this particular case, how many variables do we have? We have 1, 2, 3, 4, 5, 6, 7, 8 variables. 1, 2, 3, 4, 5, 6, 7. So we have 8 variables. But here we will use the Buckingham theory which says that the least, if you identify the least number of independent units, let's say the least number, if least number of independent units is n, then you will work, therefore, in that case with, therefore, work with 8 minus n, so you'll be left with 5 variables. Remember, we are normally used to 3 variables. We are normally used to 3 variables. Normally, talk of 3 variables. Talk of 3 variables. That is length, mass, and time. But now we're talking of 5 variables. So that we can now write our equation. We can write our equation. We can write our equation. We can write our equation in form of those variables. We can write h in terms of the variables. We have said these are our variables. Those are our variables. And to apply this particular equation, the group of these variables must be dimensionally homogeneous. So the variables must be dimensionally homogeneous. Remember, when you're dealing with phases, when you talk of homogeneity, that's a state of matter which is uniform throughout. State of matter which is uniform throughout. So in other words, these variables should have some harmony in terms of their units. Therefore, we can write h here is being equal to A, okay, C, the theta, L, coefficient 1, 2, 3, 4, 5, 6, 7 plus B, okay, theta, B1, B2, B3, B4, B5, B6, B7. So we have these indices A1, A2, A3 associated with these particular units or particular quantities. And so what are we saying? They are dimensionally homogeneous, and therefore we are able to actually write them as a sum. It can be an infinite or a finite sum of these terms. Can be written as a finite or infinite the terms. So we have written them. So there could be C, again, D and E and those quantities and those indices. Now let us look at the table. Let's look at a table. Let's develop a table. A table of the unit. And in this table, we will have their dimensions. So in this particular table, we'll have mass, we'll have length, we'll have time, we'll have temperature, and we'll have heat. And of course, we have the units. We are now familiar with all those units. So, we go back to our units, which become very, very important. Our units become very important. Now, H we had said was watts per meter squared per Kelvin. And what is watts? Remember, is joule second. So we have that joule second, meter squared, Kelvin. So joule is heat. We have second, which is time. Remember that one we are dividing. Meter squared, so that's the unit of length. K is temperature. Again, we are dividing. Mass is not there. So 0. We're developing the second table. For mu, we said it was Newton second meter squared. Newton is force, and that's mass times acceleration. Per second squared Newton, mass times acceleration, times second, meter squared. So that they cancel with meter second. So we have mass is 1. We have meters, that's length, minus 1. Second, that's time, minus 1. We don't have temperature. We don't have heat. Density is mass over volume. So mass, in density, we have mass dividing by volume, which is length cubed. So minus 3. The rest are not there. Then we have K, which is thermoconductivity. K is watts per meter per Kelvin. Again, watts is joule second. Meter Kelvin. So for K, heat is 1. We are dividing by time, minus 1. We are dividing by length, minus 1. Temperature, we are dividing, minus 1. So we have temperature minus 1, length minus 1, time minus 1. There's no mass, that's 0. CP, specific heat, is joule per Kelvin per kilogram. So we have 1. We are dividing by mass, it's minus 1. We are dividing by temperature, 1, that's a 0. Temperature, there's no mass, so you just have temperature 1. All the other quantities, the other dimensions are 0. Fluid velocity is meter second. So fluid velocity length is 1, mass 0, time minus 1, 0, 0. And then we finally have length. The characteristic dimension L is simply m. So length is 1, less than 0, 0, 0. Very important for us to note those quantities. So you need to know the units. It's very important for you to know the unit. And so what do we have here? So we want to set up the equations for mass. The equation for mass. Remember, we had h as a function of these quantities. Remember, we had h as a function of those variables, function of these variables, from mu up to, we have put L, remember. So for mass, so therefore we have 0 for h is 0, and let us use the board mass. H is 0. Then the first, remember, we had A1. We had A1. Those are those, remember, for this particular quantities, A1 times 1 the other one plus A2 times 1. The other one is A3 times 0. The other one is A4. A4 times 1, 2, 3, 4, the fourth coefficient, minus 1, plus A5 times 0, plus A6 times 0, plus A7 times 0. So for this particular one, it is A1 plus A2 plus A plus minus A4. The rest are 0. When it comes to length, we have for length, h is minus 2. So minus 2 is equals to minus A1, we are multiplying by minus 1, minus 3A2, minus A3, A4, that is 0 times A4 is 0, 0, then 6 is plus A6 plus A7. The other one is time. H, time is minus 1. Minus 1, so it will be minus A1. The other one is 0. For the second one, for the third coefficient, be minus A3. The rest 4 and 5 are 0. 6 is minus A6. Seventh one is 0. The one for temperature, let's consider for temperature, H is minus 1. First coefficient is 0. Second is 0. Third is minus A1. You are multiplying minus 1 times A3. Fourth is 1 times A4. Fifth is 1 times A5. 6 is 0. 7 is 0. Finally, heat will be H is 1. That is equals to A1 is 0 because multiplied by 0. A2 is 0. A3 times 1 plus A4. And the rest are all 0. So these are simultaneous equations. You are going to have, we have how many simultaneous equations? 1, 2, 3, 4, 5. So we have these linear simultaneous equations which you need to solve. So you solve for the 5, for to 5 linear simultaneous equations. And it's not a big deal. It's not a big deal. These are just linear simultaneous equations. For example, one which is very fast to work with is just add, if you add temperature, example, if you add that temperature plus heat expression, if you add temperature plus heat expression, it becomes minus 1 plus 1 plus 1 is equals to minus A3 plus A4 plus A5 plus A3 we have that plus A4. And you're going to see that that will cancel out. There's a minus which you have forgotten somewhere. It should cancel out. One of these is minus. So that should cancel out, or that is minus. You have not checked in your table, and that should be 0 is equals to A5. That for temperature and heat. Temperature and heat, there's a minus sign we have missed out somewhere there when I was writing the expression for heat and temperature. Because remember, we have heat in that particular portion there. That is A3, A4. You look at the table, there's somewhere where we have one of the A4s is a minus. So you can sort that out, look at it in the table, but you'll find that A4 cancels with that, so you get A5. And you can continue with this particular process. But these are just linear simultaneous equation. You just remove one, fix it in the other equation, and keep narrowing it down until you get a solution. So we can actually narrow down and say, let us focus on a group, on particular fundamental units. Let us say focus on groups, so that we can focus on some fundamental unit on velocity and specific heat. And just remember the dependency of some of these things. For example, when it comes to temperature, the units are a bit amorphous, because, for example, you can have temperature in terms of its coefficient, in terms of transfer coefficient. You can have it as that particular one. Temperature is involved in all that. So you have to rationalize this. You have to use good judgment to be able to figure out whether it's a fundamental unit or not. So it's important for one to look at some of those particular quantities. Therefore, we can focus on velocity and specific heat. That is lump those groups to do with velocity and those groups to do with specific heat. If you remember, we had said that our H was A. Then we had the dynamic viscosity, we had the density, we have the heat capacity, we have the fluid velocity, and we have the characteristic dimension. So we say this was A1, A2, A3, A4, A5, A6, A7. So we can pick on this to do with velocity. Those will be the ones lump down the A6 the coefficients and the specific heats. So we lump up the A6s and A4. Sort out those particular groups. And so in a nutshell, what are we saying? So that when we come back to our quantity here, we just focus on the A4s and the A6. And so we can actually reduce this quantity. H is equals to A. Now, remember the Nusselt number was HL over K. So, if we multiply H by K over L, this is K over L, and we multiply this side by K over L, then we can have our quantities which we have said we focus on this group of the specific heats and the group having the velocity. When we do that, then for the specific heats and velocity, and for specific heat, the quantity which you have, and this, remember, is the Reynolds number. And this is thermoconductivity. A Prandtl number. That is Prandtl number. Very important for us to remember. So we have just lumped the velocities and the quantities dealing with specific heat. And so we have these particular expressions. Just go through the linear simultaneous equations, put them in, solve them in terms of, solve those linear simultaneous equations. Note, solve the linear simultaneous equations in terms of the velocity, that is A6s, the indices A6, and specific heat. This is A4. And so if you do that, you are able to simplify that expression where we had those indices and the likes. So you come up. So remember here we have the velocities. Notice